everybody, and welcome to today's webinar. My name is Lisa Schultz. I'm the Marketing Manager for Clustrix, and I'll be your moderator today. Our topic today is Beyond Aurora, Scale-out SQL databases for AWS. We'll get started in just a few moments, but first we wanted to start off with a quick poll. So if you don't mind filling in your responses, that'd be awesome. And while you guys take the time to fill that out, I'm going to touch on a few questions that people typically ask. We will be emailing a link to the recording as well as the slides from this morning's webinar as soon as they're available. And also we'll have a Q&A session at the end of our webinar with our speaker, and then we're also going to have two other Clustrix employees jump on at the time so they can answer any Clustrix-specific questions. So make sure if you have any questions that come up during the presentation, you can just fill them into the chat window, and we'll take them at the end. Our speaker today is Lokesh Khosla. Lokesh is the CTO of Magnus Data, a Boston-based consulting company focusing on database projects. He brings with him more than a decade of experience in implementing databases and analytic solutions, and we are excited to have him. Lokesh, why don't you get things started?
Thanks, Lisa. Hello, everybody. So like Lisa mentioned, today we are going to be talking about we'll be discussing about the scalability, application scalability issues, which are generally seen on the database side. And for some reason, Lisa, I'm not able to get out of the poll.
Yeah, I think you need to share your screen again. And then it'll show.
I am actually sharing the screen. Can you see the screen or not yet?
Not yet.
Okay. Apologize for. Okay, let's try now. Share.
There we go.
Okay, sorry about that, guys. So quickly jump into talk a little bit about Magnus Data. We are a consulting company specializing in the database world. We do big data implementations on anywhere from OLTP to the analytical sides for high performance applications. And today what we want to talk about is we'll start with the market landscape of the database market. We will talk about the different options which are available to scale the databases. How are some of our customers who are actively trying to scale the databases, what are the techniques they are applying, what other solutions are available out there. Specifically, we'll get a little deeper into the scale-out architectures and what are the benefits there. And then finally, we'll touch base on the comparison of the solutions for high transaction relational databases, primarily focusing on Clustrix DB, which is the product from Clustrix, and AWS Aurora. So there's a benchmark comparison which we'll look into more deeply, which was done by us. Okay, so talking about, just to set the stage, traditionally what we have seen is the general purpose database market, or the traditional databases, covered the whole spectrum of the workload on a database. So either it is a transactional database workload or analytical workload. These are two wide spectrums. And in this picture on the left-hand side shows the transactional side of things. On the right-hand side is more analytical workload. And traditionally, one particular database would be doing any of these workloads. And eventually, over the years, customers realize that one size doesn't really fit all. You really need specialized databases for each of these categories. And then you started to have these new categories come in. For example, the new SQL or the operational system OLTP side of things. Then there are some NoSQL databases which have come out. And on the analytical side, we have MPP, shared nothing architectures, columnar appliances, and then finally Hadoop, which is on the analytical side again. Today's focus is primarily on the operational system, which is the OLTP, transaction processing, also known as the new SQL category. So we'll be going specifically in that particular trajectory. Generally, what we see is whenever there is a database scalability issue, customers have two options available to them. One is the scale up, and the other one is scale out. We will go deep into each of them. But for now, to show you on this graph, what we are trying to show is in the scale up, what we see is adding more hardware or memory or pieces of the hardware into an existing database server gives you the scale up option. The problem with that is that you can only scale up to a certain limit, and the latency for as you scale up, it gives you a relief, but generally the latency still keeps climbing up for the response time. While on the scale out transactions, the goal is to keep the latency pretty much what meets the SLAs and keep scaling out the database cluster by adding more nodes. So let's get started and understand what are the different scaling techniques for the scalability issues. So the first one, which we talked about, is scale up. The second one, master slave, master, and each of these categories, depending on what the application is, the customers are either trying to use one of them or trying to solve the scalability issues by choosing one of these options available to them. The last one is scale out option, and we will get to the scale out, but let's dive into the scale up as the first one. So scaling up, what really means is that let's increase the size of the database server. That's at the high level. That's what most of the customers realize, that okay, the scaling issue seems to be on the database side. So what can I do without changing much of the application code, and I can still get my latency up? Keep the latency low. And the easiest thing is let's add more hardware to the existing server and point the application to the same new server, and I get more performance out of it. So the pros are very simple. There's no application change in this solution. The challenge though becomes is that it is expensive. At some point, when you keep adding more and more hardware, the amount of money you're spending to scale up the system, the performance you're getting out of it is not equal. And so, for example, if you may add double the number of processors or double the memory, but that doesn't really mean that you're going to get the same amount of performance out of the system. And eventually there is a wall which customers hit when they keep adding the hardware, and you cannot really scale up after a while. So that's on the con side of things. So it's simple. It gives you a quick return, but eventually the wall is still as the application needs more and more resources from the database, you start to hit the wall. The second, the most common one which we see is, well, let's take an application, look at the read and the write workload. How can we take the database and create a master slave? So that means primarily the writes go to the master, the reads start to go from the application to the slave server. And this is, again, reasonably very simple to implement. You can simply add one more server, have that as a slave to the master, and your reads are now starting to go towards that to the slave. And while the writes are still going to the master, you get more resources out of your existing master node, and the workload of the read starts to go onto the slave side. The challenge here is that if the application is very read only, specifically bottlenecked by the read performance, then it can add value. But most of the applications in the real life are actually mixed workload. They're not really just doing the reads or just doing the writes. So read performance can be added pretty easily in this, but the write, when it comes to the writes, it still is a challenge because writes are still going to a single node, which is a master node. So overall, it'll give you some relief, but again, it doesn't really provide you a holistic solution. The third, the most common one where we see is that, okay, now I want to scale the writes also. So what I do is I spin up another master. So I have two masters, and in this case, the write scaling without the needing of sharding or doing unnatural acts becomes pretty simple. So I add one more master node. My application can simply point to both of the masters, and my writes are happening. So I've divided the writes from onto two masters, so getting more scalability out of it. So in this case, again, if you have a true mixed workload, the customers generally see that it does add the write scaling, but the read slaves, if we want to add more read slaves, it will keep adding more latency into the for the read queries. And to be able to achieve something like master-master, ultimately you do need to do application changes so that you can ensure that there is data consistency, conflict resolutions. Those kind of issues, they get into the application code, and application becomes responsible to make sure that those are met for the database side, which actually the databases are built to do out of the box. And this one is a very common scenario which we see over and over again, that our customers are trying to do sharding. Sharding is basically when we pick up one particular database and we say, okay, let's bucket it, and the application is going to write to different servers depending on the buckets. So for example, in this slide, we say, okay, everything between A and K goes to shard 1, L to O goes to shard 2, so forth, so on. And you can, the application scales really well because now the writes are going to all these shards across different nodes. But it comes with a very, very heavy cost when it comes to the amount of changes on the application sides are needed. So for example, if I want to do ACID compliance, the application has to make sure that the data is consistent, durable, and it is committed across all of the shards at the same time. The backups, the restores, how the manageability, the operational aspect of all the shards become a challenge. And then of course, depending on what the application is, depending on what and the amount of writes are coming, it may be that one of the shards is more skewed, and the reads and the writes, depending on your workload, it may be going, 60% is going to one particular shard, which defeats the purpose of doing something like this. So there's no distributed query processing engine sitting on top of these shards unless the application itself is writing that layer. And that is a pretty involved and complicated layer. So all these solutions which are being used by the customers, or at least being tried on, they do come at a very, very heavy cost as you start to keep going down each of these solutions and start to vet them. In this specific case, what we have seen over and over again is that the application changes are very, very significant because you cannot, if you were running with one single MySQL or one single RDBMS host, and now you want to create shards out of it, the application has to actually change very drastically to be able to use the different shards behind the database. This one is not a very common one where we have seen the MySQL cluster. It keeps coming up once in a while, but the basic idea is very similar to to having a multi-master model. It does give you resiliency. It gives you a high availability and high throughput. But again, it only supports certain isolation levels. So it's again not a very holistic or the comprehensive solutions. What we have seen in customers is that long-running transactions are generally blocked by a node restart. So for example, if you have a MySQL cluster, you may see that one of the nodes have to restart it. At that time, if you're running the transactions, we see that they can be blocked and they have to be replayed once the node is fully restarted. So if you're looking for high availability kind of environment, this solution generally doesn't really work very well. We do see that application workload partitioning happens where a lot of companies are producing the pods, where a pod have application servers as well as the database server as part of the whole pod. Works well if you have multi-tenancy, and that's what we want to go. The challenge really becomes what happens when I am looking at across all my customers. So for example, the same app is running on 10 pods. Now I want to look at the data across all of the pods. That layer has to be written custom. It gives you, and then it does come with all the backups and the manageability issues also, because each pod has to be backed up independently. And depending on, sometimes one pod may be going after multiple customers. So it's relatively complex to actually manage it. And then the data consistency issue across the pods becomes a challenge for the application too. Maintenance side, I already talked a little bit about that. If I want to have the maintenance of the pods where I want to take the backup or restores or optimize it, I have to make sure that we have to push it across all the pods wherever the patches are to be deployed for the tuning purposes, for example. The querying and reporting becomes very, very complex unless you take the data out of all the pods and put it somewhere in the centralized location. From the setup perspective, it is not an easy, some of our customers are investing a ton of resources in just on the operational side of things to set up the environment and support it for similar implementations. So as we looked at all the solutions, what we see is that the three major criteria which customers are looking for: capacity, elasticity, and resiliency. What we find is that the common theme where we see is that when it comes to these three features, which most of the applications, the critical applications, are looking for, none of these custom techniques or the solutions really provide you elasticity, resiliency, or application impact. And as we go in the sequence of what we talked about, scale up to sharding, what we see is as we start to move down the chain where we're getting more performance out of, for example, sharding will give you the best performance for reads and writes. The challenge really becomes is that the application changes are very, very significant. So for example, Scaleup has the least amount of application changes, while sharding will need very high and will have a large impact on the application. So these solutions can be implemented, and they are being used by the customers. Soon the customers find out that the amount of time they're spending in really managing the database technique to scale the databases is really putting a tremendous amount of pressure on the operation side or the application side. And that's our next topic, that how do we resolve that, or what are the solutions which we have seen which actually fix these out of the box. And that's where scale-out architectures come in. And scale-out architectures generally give you the elasticity, resiliency, and application impact to almost none. We will get into the scale-out architectures to discuss now what and how they achieve that. So at this point, Lisa, do we want to do the next poll?
Sure, let me throw that up there. Just 1 second. There you go. Go ahead and take a moment and fill out the poll, and then we'll get back to the rest of the presentation. All right, go ahead and I think you can reshare your screen again, Lokesh, and we can wrap that up.
Thank you.
Thanks.
Great. Okay, awesome. So let's get into the architectures of Scaleout. The Scaleout architectures are generally having multiple nodes tied together over a network, which is their intercommunication layer. So it looks like a single database server to the application. The application doesn't really see the complexity behind how the cluster is architected. Each of the node, which is nothing but a server, virtual server, or a physical server, each of the node actually acts. It is running a query parser and a planner where it can accept the queries or the requests from the applications. It has the metadata. Some of the technologies call it a data map. Each of the node has the metadata about the data across the cluster. So when you load the data is actually fanned across using intelligent distribution, which we are going to talk about, across the nodes. And each of the node is aware of where the data is. Each of the node is also running the database engine, where all the database operations can be fulfilled. And finally, to take an example, when you take a large table, let's say it has 1 billion rows, and let's say you have a 4-node cluster, it will be fanned out across the 4 nodes, and eventually the idea is to get around 250 million rows on each of the nodes so that it's balanced. And all that complexity is handled by the database. The application doesn't really need to know where do I put the data to get the maximum performance. The billion rows will be automatically managed, rebalanced, redistributed across all the nodes by the database at the time of ingestion. So the takeaway from the slide is that even though it has multiple nodes, but for application, it looks like a single server system. So application can connect to any of these nodes, and application may be connecting to node 1 and requesting the data from node 2. The database will manage. It'll take the request, and it knows that I have to go and get the data from node 2, and it will get the data and ship it to the application, and application doesn't have to really do anything outside that. So how is the data distributed across the node? It is intelligent data distribution, where the tables are automatically distributed across all the nodes. So when you create the table, it automatically says, okay, I have to take this table and I have to use all the nodes for this table. And the data is redundant. So for example, for resiliency, for high availability, the system automatically auto protects the data by making a copy of the data. For example, node 1 data may be on node 2 or node 3. It manages itself. But it gives the user an ability is that where you can say, well, I don't want one copy. This is a highly critical application, so I want the redundancy or the copy of node 1 data or each of the data set to be more than one. So you can configure it inside the configuration file, and when you load the data, it creates that many copies, manages them, and in case of a node failure, it reads from the redundant copy and rebuilds rebuilds a new node if you add it. If you don't add the node, it will still keep servicing the queries and the request from the redundant copy. So this animation basically showed that, as you can see here on the picture, the S2, one of the slices, is copied over from node 2 and from node 2 into node 1, and you can see that each of these slices have a copy which is maintained by the other node. So in case of resiliency, it can automatically recover without going down, and the DBAs or the operation guys don't really have to worry about going to the backups and restoring all of the database. Distributed query processing. This is another big factor, which generally we see a lot on the application side. For example, in case of sharding, where you have a sharded database, now the application is responsible to really find out where the data sits and how I'm going to process the data, how I'm going to join the data between the two shards, or more than two shards, for example. In this case, the query processing engine is actually already built into the database. So when the application connects, it is still connecting, thinking that there is a single server. It connects, fires the query. The query is intercepted by the planner optimizer. It looks at the queries. It splits it into multiple steps. And then it says, okay, I need to be able to fulfill this query, I need to send this query to be run on node 2, node 3, and node 1. It will split into the steps. It will actually ship those steps onto each of the nodes, and the nodes will process data, and the data will be shipped back to the application. Now, all the nodes in case of scale-out architectures, all the nodes can handle reads and writes. So you can actually attach it to any application can send the same request to any of the queries, any of the nodes. And the results which are returned by the query are aggregated and returned to the user, and the application doesn't have to really worry about, do I need to do a final aggregate, or do I need to do more processing on the data for the aggregates, which is generally the case when you're doing sharding and joins over shards. In this case, you don't have to really worry about it. So what we see is, we talked about the capacity, elasticity, and resiliency. What we find is a comparison. Aurora is one of the Scaleup solutions, which is from AWS, and Clustrix DB is by Clustrix. Clustrix DB is a scale-out solution, and when we did the benchmark, which we are going to be getting into a little more in a couple of slides, we wanted to see how do each of these technologies, we tested the technologies for the capacity, elasticity, and resiliency, and what we found is Aurora does help. It does help from the MySQL perspective, that if you have a MySQL server, it can help in scaling up more writes. But it does have, because it's a scale up and not a scale out architecture, it does have a wall where it starts to hit when it comes to the writes. After a while, it cannot add more writes to the scale up architecture because of the scale-up architecture. Both are ACID compliant. Aurora does not have on-demand write scale. So what that really means is, in case of Clustrix DB, you can keep adding the nodes and taking away the nodes if you don't need that capacity. While on the Aurora side, there is no such option available. It's a single host, single nodes solution where you can add the replicas for the reads, but for the writes, there is no way to add more capacity for that. When it comes to being on the cloud as well as on premises, the Clustrix DB is available on the cloud as well as on premises. Aurora is available only on the cloud. The final thing which we saw was that shared nothing storage, which actually provides you a lot of scalability when it comes to writes. Clustrix DB has a shared nothing storage. On the Aurora side, we see that because it is a shared storage, the contention when the concurrency is very high, the contention there is a lot of contention, which basically means is the latency starts to go up for your transactions if you have high concurrency on Aurora side. The workload, the high concurrency workload perspective, what we see is latency remains very even in ClusterXDB as we scale out more and more writes and we throw more concurrent transactions at it. While on the Aurora side, the latency actually starts to climb very quickly with high concurrency. Okay, so these are some of the benchmark results which we took the sysbench OLTP 9010 mixed workload, we tested Clustrix, Aurora, and MySQL RDS in the cloud. And what we saw was, the goal was to see at what point does the average latency for each of the transactions starts to climb up in each of these environments. And we wanted to see generally less than 10 milliseconds or under 10 milliseconds. And what we saw on the x-axis, what you see is how many transactions per second are we putting into the system, and at what point does the latency start to climb up and go beyond 10 milliseconds. As you can see, I don't know if hopefully you guys see the same colors, but the yellow line is the Clustrix line, the red line is the Aurora, and the gray one is the MySQL RDS. And what we found is that the Clustrix was able to get to around 10,000, just a shy of 10,000, around 8,000 transactions per second and keep the latency under 10 milliseconds, while as we added more and more transactions, more concurrency, the latency on Aurora and RDS started to climb up pretty quickly. And the next slide is actually going to talk a little more about the scale-out architecture of Clustrix, where we added more and more nodes, ran the same test, try to keep the latency again below 10 milliseconds, and we see that as we add more nodes, we can actually linearly keep the latency under 10 milliseconds. And here's the slide where we added more. So we ran the ClusterXDB with 4 nodes, 8 nodes, 16 nodes, and 20 nodes clusters. While on the Aurora side and the RDS side, there is no such option available because they are scale-up databases. And what you see here is because they are scale-up solutions, as we added more transactions or transactions per second with more concurrency, the latency starts to climb up very quickly. While it did happen on Clustrix side also that the 4-node system was starting to climb up, but then we added more nodes and we ran the same workload, and we can see that the number of transactions per second went from just a shy of 5,000 to 7.5 thousand, and as we kept adding nodes, we could scale the transactions and keep the latency to our SLAs. So what we saw over and over again is that on the scale-up solution side, we start to hit the wall. Even if we added more and more hardware, we started to hit the wall very quickly when it came down to latency and adding more transactions per second through many concurrent threads. While on the Clustrix side, we were able to actually add more nodes and scale it pretty linearly. Okay, I'm going to send it back to Lisa, and we can take Q&A.
Great, thanks Lokesh so much. And as I mentioned, we have Dave Anselmi, Director of Product Management, and Peter Friedenbach, also from Clustrix. So they'll join us in answering some questions that you guys have, if they're Clustrix related, and then otherwise we can jump in with the question and answer for Lokesh as well. We do have a question here, and it looks like the first one is, does Clustrix shard?
Hi, Lisa. This is David Solmi at, I'm sorry, Lokesh, did you want to cover that one?
No, go ahead. It's Clustrix specific, so why don't you go ahead and answer? Go ahead.
Sure. Sorry about that. Okay, so that is the primary question everybody asks about a database kind of like this, is that how do you get that right scale? And as Lokesh carefully and elaborately showed, there's different ways of approaching scale, and only a couple of them can handle writes. And so everybody assumes, oh, write scale equals sharding. And so Clustrix is literally designed to avoid the issue of sharding for the end user. So the two main issues of sharding is you have to pick that partition key, and then you got to manage the data across those different servers. And the third part is, ideally you can consider it the worst part, is there's no real relational database management system master that controls all the different separate partitions. So if you just had a partitioning database system, you'd have different tables on different servers, and still with one RDBMS maintaining the referential integrity and consistency between those. But when you shard, each of the partitions, if you will, is on a completely separate RDBMS. So now your application is unfortunately put in the position of maintaining that kind of relational and referential integrity, relational consistency, ACID at a transactional level. Everything is done by the application side. And unfortunately, the application developers effectively have to reinvent the wheel. So you have these three main issues. You have a relational database master system that doesn't exist in sharding. You have the ability to pick the correct partition key so the data doesn't get lumpy. And then when the data does get lumpy, inevitably, you have to move the data around in the background. So Clustrix's answer to all of this is, number one, the data is automatically sliced, as Lokesh described. That means it's automatically hash distributed across different slices across different nodes, which means that even though you add additional data in the range, it isn't range distributed, so the data is constantly being separated through a hash. And it's consistent as well. So we always know where the data is going to reside, and as soon as the data gets a little bit too big for that node, lumpiness if you will, we have a patented rebalancer, actually two patents on the thing, which will automatically grab the data, reslice it, and redistribute it across the separate nodes. And in the third issue of having a master RDBMS, there's only one RDBMS. When you take your application that's been currently pointing at a stack similar to MySQL or MySQL itself, and you point it at Clustrix, your application doesn't need to know that you're pointing at simply one RDBMS. It still looks at one RDBMS and is automatically giving you full scale out of both writes and reads.
Thanks, Dave. Looks like another question came in actually, Lokesh, during your presentation around, I think it was on the comparison chart that you had against Clustrix DB and Aurora. And that question is, why didn't Amazon do a better job with this, and are they going to get there?
Well, so it's so very hard for me to answer. I can only take a stab at it. Whether they're going to get there or not, to create a scale-out architecture is actually very hard OLTP problem to solve. So in OLTP world, solving a scale-out architecture, creating a database is not a very simple thing to do. You need to have your own internal communication links. You need to have your hashing algorithm, the balancers. So I think there are not too many companies out there who are taking the approach to solve that problem because it's a harder problem to solve. Will Amazon, do they want to focus on that? I'm not sure. It's going to be hard for me to speak, but my take is that these are, because they're hard problems to solve, and to get to the market, maybe they wanted to get out and just scale the existing MySQL to get to the Aurora and give you a little bit of performance improvement. But I think the solution doesn't seem to be that it will scale to any length. So maybe they have some plans which we are not aware of.
Great, thanks. Another question. The Aurora benchmark said it was 5x faster than RDS MySQL. What's up with them being comparable in this benchmark?
So, I'm sorry. Is the question about Clustrix versus Aurora benchmark? Is that what we're talking about?
It looks like, I think
do you want me to
Aurora
weigh
actually
in
had
on
a
this?
benchmark. Sure, that sounds great, Peter.
Yeah, so this is Peter Friedenbach. I'm a performance architect here at Clustrix. Aurora, when they published their numbers, they actually they published a slightly different workload than what we published here. But what they were going after were really peak performance numbers. And I believe when they really got to their peak performance number that they published for their side, that's where they got the 5x performance over what they claim were comparable MySQL numbers. In the charts that we were showing, as you see the graphs, you start to see the graphs try to differentiate themselves as you basically crank up the workload, but you're getting a lot higher latency times in there. If you extract it out to the points that Aurora would have been claiming performance at, I think that's where they got their 5x number to MySQL.
And I think, Peter, it may be fair to say that in real life the workload is actually generally you see mixed workloads, basically reads and writes. I'm not sure Aurora 5x, did they run the mixed workload or only just the reads or the writes?
No, they actually ran just reads and writes. And let me make a couple of comments here, I guess, because I do get this question a lot of why did we not run, let's say, the suspense the way Aurora ran it? Why did we do things differently? And I think there's three big points that we tried to avoid that we think are problems with the way that Aurora actually ran suspense to do their tests. One of those points is mixed workload. Aurora went after a pure read number and a pure write number. The problem with their pure read number in our experience in kind of running their product is they got a very aggressive high read number, but as soon as you start entering writes into that system, they start taking a more disproportionate hit to their performance than you would expect. And real applications are read-write environments. But the other things that we found that we tried to avoid in doing these numbers is, second point was really on data size. If you actually look under the covers and look at what Aurora ran, they're really running with very small amount of data. I think it was 6.25 million records total of data in their database. Our results are using 40 million records. We think that's more representative of the type of table sizes you'll find in this OLTP world that we're in. But lastly, and the most important thing that kind of pulls out on the graph that was earlier is we think latency really matters, and that customers that are looking for products in this space should be looking for low latency too that should be delivered. And in our world, we believe we got better latency, on a core-to-core comparison, which was really the first slide you put up there against Aurora. But the other thing we have going for us is because we're a scale-out architecture, we can continue to scale out our environment to try and maintain low latency. And the only way you're going to get peak performance in the scale-up architecture is basically taking it at cost on latency. So anyway, a couple of comments on the benchmarks. Back to you,
Great,
Lisa.
thanks. Another question came in, and it's, can a cluster be geo-distributed?
I'll pick that one up. So a cluster, and when you talk to geo-distribution through the different offerings in the market, they talk about having different nodes at different locations, like for example in different regions on Amazon or in different geographic locations like in different countries. So a cluster, as we define it at Clustrix, is 3 or minimum of 3 nodes, and they're all with a very high speed interconnect. So we can distribute between clusters in different locations, but putting those nodes on different, like for example, countries is going to make for a very, very slow cluster. So basically at the end of the day, you're always going to have E equals MC. You're going to have some kind of limit with the speed of light.
Thanks, Dave. Also, how can Clustrix scale both reads and writes without sharing? Sharding. Excuse me.
So I already covered the two parts of this. Well, actually, I covered the first part of the two parts of this. The first part is we do the slicing, we do the automatic redistribution with the rebalancer, and in so doing, we maintain the referential integrity with a single RDBMS. So that's the first part. So we're able to automatically slice the data. So similar concept to sharding in the sense that the data is distributed across nodes. as opposed to, for example, RDS system, which includes Aurora, which includes MySQL and anything else on there. It's all shared storage. And so as Peter was suggesting, they have even worse latency we'd expect, but even the people at Amazon admit you're going to have latency when you have a mixed workload on a shared system. So shared storage means that when you write to a row, that row is locked and the reads can't read from it unless they read from a previous version. So depending on what isolation level you have, you're going to have some kind of latency built into the product. So with automatic distribution across nodes, you don't have that shared storage issue, and so that latency disappears. So automatically having your data distributed across nodes, that's the first half. The other half of it is, we call it bringing the query to the data. What we do is the receiver of any of the queries that comes in, and all the nodes are equal, so there's no leader node, there's no single point of contention here. Any of the nodes picks up that query. The query is automatically broken into its component parts and precompiled. So those precompiled component parts of the query, functions if you will, are sent directly to the node in which the data resides. We know where that data is because of the consistent hashing, so we don't have to do broadcast. And any of those functions are sent one hop to the nearest node. Now, we described 3 nodes. We have nodes in clusters of 30, 40, 50 node sizes. And each of the hops is a single hop. And then it comes back to the originating node. So it's a combination of our splicing technology, rebalancing technology, and the ability to bring the query to the data. It allows us to scale out.
Great. And the listener who asked about the clusters being geo-distributed also asked if you can comment regarding Clustrix for analytics.
That's a great question, and actually I'll say a couple words and I'll punt it over to Peter when he talks about we're looking at different benchmarks for analytical benchmarks. So one of the things that we like about our cluster a lot is that we handle OLTP and high-frequency transactions, but at the same time we can handle analytic workloads on the same data. We have people in production currently right now, even during huge peak workloads, they'll be doing A/B testing to say, hey, for example, an e-commerce site that says, oh, I'm putting the sale on, a flash sale, and is this red button going to work or is the green button going to work? And then they partition their users, and they give some of them red, some of them green, and did analytics right there, right in the real time to determine which one was better and change their system. So the way we're able to prioritize this, we have what's called the fair scheduler that knows how to prioritize OLTP transactions versus analytic transactions. Now, as a pure analytics play, you're not going to get Hadoop type of functionality out of us. You're not going to put thousands of nodes. And on the other hand, Hadoop doesn't want to have a strong consistency between all the nodes. So something in between, though, like a data mart size, we work with very well. Up to tens and tens of terabytes, we're fine. So Peter, did you want to talk about a little bit about some of the YCSD benchmarks that you're looking at?
Well, actually, that's not necessarily directly on analytics. That's more kind of in the NoSQL space, where we actually think we're getting some pretty decent performance things that we'll talk about at some point in that space. On the analytics side, one of the powers that we have coming into this thing is we are a general purpose relational database. So while we're geared towards high performance in the OLTP space, we can handle the complex queries that come through from the other side. Now, having said that, there are vendors out there that have products that are very specific to analytics, but you're not going to run an OLTP workload through them at that point, and if you're really geared just specifically to analytics, you probably need to be looking elsewhere. But if you're looking at having data, having transactional work coming through it, but then running queries against that data in some real-time fashion to do actions on it, that's actually what we're kind of geared towards, what we're trying to market ourselves to and what our technology is capable of doing.
Thanks. Looks like we have 2 questions left, so feel free to write into the chat window if you have anything else that pops into your head during this time, but we'll be wrapping up shortly. So the next question is, what is the maximum number of servers you can have in a Clustrix cluster on AWS?
So we have QA spin up 30 node clusters. We have benchmarking. We've run 40 node clusters. And in-house, we've done 50 and above. We have quite a few more than 50. But at Amazon, we target the 2XL size. So it's not a huge outlay, but when you start making the huge clusters, you watch your wallet starts opening to Amazon. Now, Peter, did you have anything more to expand?
We We've tested I've tested personally up to 40 nodes on AWS. We can scale further than that. That's just the range that we've actually tested at. Because we're a scale-out architecture or whatever, if you want the choke points that would cover us on the scale-outs are much higher than that. As hinted at, we tested at more than 50 nodes internally. So.
Cool. And the next question is, I've designed near-time analytics using similar models. What's the bottleneck on number of servers and commonality between servers? Communication between servers.
Yeah, it is exactly that. And then I'll let Peter answer that more fully. But right now, I have to say, Amazon has the best, their enhanced networking. They have the best networking in the cloud. So we've tested thoroughly many of the clouds out there, and the one that handles networking the best is them, and so it's not nearly the bottleneck on them as other clouds are. But Peter, do you have more input on this?
No, I would agree with that statement. So yeah, at some point the network will become a bottleneck on our environment. But as we've seen, actually the enhanced networking feature that Amazon put out last year actually is rather impressive what we can get between the nodes on an Amazon cloud. On the other side, internally we've run networks and run clusters and stuff that if people deployed not on the cloud but deployed internally, we potentially had capabilities of pulling together 10G networks and stuff between boxes to address some of that space as we got to really big clusters. But in our current environment and the testing that we've done on Amazon, that's using their enhanced networking environment, which we think is pretty capable today.
Great. And the last question is, how difficult is it to get clusters up and running on AWS?
That's a very interesting question, yes. We have two different paths right now, obviously, and there's the command line path. But we have an AMI, and so you just ask us for a trial license, we'll give you an AMI, and we'll walk you through putting it together. We're actually working with the Kubernetes framework, and so stay tuned. In the next quarter, we'll have a Kubernetes. Literally, you type in your Amazon password and press a click, and you'll be deployed. But right now, AMI, and you can have it with enhanced networking, as we recommend if you're performance testing, or if you just want to have a dev environment to do functionality testing, you don't even need to use enhanced networking, and you can use a different AMI.
Cool. All right, that's everything for today. Thanks again, Lokesh, for that great presentation, and Dave and Peter for joining us for the question and answers. Thank you to all the attendees as well for sticking around, and we'll talk to you next time.
Thank you.